Uh, Good afternoon, everyone. On today is February 23. We didn't reach to March yet. We're gonna start Sunday 2 p.m. To 5 almost on the next section. Uh, about this, before starting the session, I wanna emphasize two nearby items that we have. One is uh, uh, the era that we celebrate women and girls in the astronomy from February 11 to March 8. You're gonna have I gonna have some presentation with a card game that is developed by AIU International Astronomical Union and Pineville Library on March 22nd. And also we had another opportunity for the nearby Astronomy Club conference next Saturday, 3 star in the Greensboro. And I put the links over there if you want to attend to that. But the thing is that we had Saturday also, we have another session of our OPIS. Probably I may inform if everybody agreed. We just cancel those to attend that conference because it's a 1 day activity, Greensboro, and very close to the Charlotte. And if anybody wants to attend. Therefore, I'm just proposing might be Saturday morning we cancel, and therefore every one of us, whoever wants to attend, get the opportunity to go Greensboro uh, Astronomical Club and watch the presentations on that day. It is from morning to the evening, I think 1 day activity and very close to Charlotte. Okay, today discussion that we had, we are going to have is a continuation, the last part of the lab one about the tricks and kind of information that we're gonna get on the post-processing of the afterglow and also Skynet pictures. If anybody had successfully go to the afterglow and enlarge and zoom and take a picture from the afterglow and Skynet, any issue on that procedure? Also about the marking the objects and get the distance and uh, diameter, angular diameter, things like that. I hope everything is all right and everybody good on that. Any question on those afterglow and Skynet for the lab one? Okay. And that's, I think, because we are good, we're gonna let me share the screen. Mm,
Yeah, as you're
mm,
as you're setting that up real quick. So last
Sure.
Sunday we did go through the diameter and radius and how to use afterglow for those measurements and how to mark things. And so Avery, you saw that last time. Rui, you're okay with that too, with the markings and measuring the distances in afterglow? Awesome. Okay.
Very good. Awesome. Your progress is very good. It inspire me also your learning and also it's gonna be very beneficial. Next item that we're gonna go on the lab two that they had here. On the lab two, we're gonna have kind of reasoning for the Earth and season based on the Stellarium version. We're gonna look through it. And similar items exist about the submissions, about the material that you're gonna submit on the WebAssign. And also, we're gonna go over a very simple way how to describe the Earth and season. As you know, the map of the Earth, we divided based on the coordinate system that is decided about centuries ago, that how we divide a specific location on the Earth based on the longitude and latitude. And that is basically goes with the great circles on the Earth. Do you know any definition of the great circle? What is the difference between the great circle and the regular circlers? The great circle is the basically is the uh, one concept. We have two geometry. One geometry on the plane surface that we draw the circle, and one geometry we have on the face of the Earth, a kind of spherical shape like Earth that we have. The great circle is the circle that is passed through the poles. Therefore, if you have North Pole and South Pole, the circle that is circling around the sphere that passing through the North and the South Pole, plus the center, we call it a great circle. For example, equator is the great circle because it is uh, this one of the great circle that is goes from the North and South Pole and center. We call it meridians or kind of things that we measure the uh, this longitude. And the one great circle that is uh, on the center that we call it equator has the same distance from North and South Pole. We call it equator, and it is zero, we call it, for the measurement of the latitude. Other circles that is parallel to the uh, equator is a um, it is parallel to the great circles, but it's not great circle because it has become smaller and smaller when we reaching to the North Pole. At the North Pole, we become as a point. We don't have any circle anymore. There is based on this geometry, for example, in here, 0 degree on the equator, we have uh, the greatest diameter for the Earth. 15 degree, we're just getting 15 degree closer to the north, 30, 45, 60, and 75, and 90 at the end. We're going to have one location as a North Pole. Therefore, only in here, the great cycle is the equator. The other ones is the spherical cycle also parallel to the great cycle of the equator, and therefore we can check it accordingly on the stellarium. For example, in the stellarium, here, when we click at the location, for example, Chapel Hill, United States, or any other place on the world, when we search here, uh, it gives us the latitude and longitude on that city. But that is representative because a city is not a one point. We have many different points, either on the center or suburb or surrounding area. Therefore, this is the one coordinate that is decided for that. Probably we may live on the Chapel Hill, but the or coordinates is different. Right now, you may have various devices in your cell phone. You can get the GPS or various apps also. You can check it accordingly. But other than that, it is kind of things that you can check it on the your apps or your Stellarium on the app, your computer as well, based on that. When you get this latitude and longitude, you will put it here, and based on the 2 points, we're gonna have kind of consider negative for the south and uh, west longitude. For example, the place that we are in the United States, most of the time is the northern latitudes, therefore it's gonna be positive. But we are on the west side of the Greenwich, therefore it's gonna be minus. Therefore, for us, gonna be around minus 79, 80, or 81 if we are living on the area between the Raleigh and the North Carolina to the Tennessee or other places nearby. And the second item is the one we're gonna recognize two things about the solstice and equinoxes. And the equinox is a Latin word. It comes from equ and nox. Nox means the night. It means that equal night. But actually, this is meaning means that we have equal night and day on that day. For example, either on vernal equinox or autumnal or fall equinox on the start of the fall season, we all around the globe we're gonna have equal lengths of the day and night. And therefore, this is very specific for us and the start of the spring and fall. And on the other hand, the summer and the solstice, summer and winter solstice is the one start of the summer and winter. And those is the angle of the sun, the location of the altitude of the sun is going to be higher on the elevation. For example, on the summer, it's going to be higher on the sky, and on the winter gonna be lower on the sky, dependent on the location of the Earth that we are living. The reason for that is uh, due to the angle between the celestial pole and also the axis of the rotation. If you see on the regular globe that you may have seen in your home or other places in schools, the axis of the rotation is an angle corresponding to the angle, the uh, celestial coordinate on the sphere. Therefore, if we look through it here, it's about 23.44 degree or 23.5. If you see it, this is plane of the revolution of the Earth around the Sun. This angle gonna stay at the same place along the revolution around the Sun, and that gonna main reason for the seasoning. It doesn't mean that because there is a kind of in the public there is a misconception exists that they will thinking we are hotter on the sun on the summer because we are closer to the sun, or cooler because the winter we are far away from sun. Is actually reverse. On the summer on the North Pole we are uh, farther away from the winter that is closer to the sun. Therefore, the reason is here, this scale, it doesn't show very good because it shows almost most of the picture you see it on the NASA, on other educational tools. It shows a circle and the orbit is sun is on the center and orbit is circle. But actually orbit is ellipsoid. It's one area. For example, in the winter here, we're gonna have sun a little bit closer to us. And here that is summer, uh, we are farther away. The reason that is, you know why the reason we have hotter on the summer on the northern hemisphere than the winter on the southern? Question?
Because of the tilt of axis.
Yeah, it is. For example, when you see it here, if I stand it here, the sun directly impacting me on the right angle. But when I am here, the angle of the sun on the sky is lower. As you see it, you notice if you go outside right now and see it, the sky, sun, you don't look through directly to the sun, but you can see it, the elevation of the sun on the sky, apparent elevation is lower than on the summer. If you compare it 6 months later on the summer, you see the sun elevation on the sky, we call it altitude, is higher. Therefore, it shows here very good on the next example. We're gonna have it here. Let me see. Here. This picture shows very good. When sun is higher, the angle of the kind of sun rays on the earth is more closer to the vertical, but on the winter it's very aligned. The reason that on the summer we're feeling hotter on the northern hemisphere because the area of the sun rays on the earth is smaller than the uh, on the winter. When it is, for example, when it goes closer to the uh, North Pole, the sun gonna be somewhere here. Then it gonna scatter on the more area on the earth. Therefore, the intention of the warmness and the hot on that region, it's gonna be scattered on more area. Therefore, it causes less heat absorption on the surface of the earth. And that's the main reason that we have winter and summer because of the tilt of the sun axis compared to the celestial pole that we see it here. And here there is some question on web assign. You can assign, as I mentioned, longitude and latitude. And also here about if the summer solstice in northern hemisphere, what's the southern hemisphere? If we have, for example, in here, we are northern hemisphere, we have summer solstice, assume we are in this position, the sun is directly impacting the surface on northern hemisphere. What is the southern hemisphere we have? We're gonna have summer solstice also?
Winter.
It's gonna be reverse because the reason is that if you notice summer southern hemisphere, the angle of the sun rays on the surface gonna be in angle compared to the summer in here. Therefore, whenever we have summer solstice, the southern hemisphere on the Earth gonna be winter, and reverse. When we have a winter solstice on the, for example, Chile or Australia, gonna be summer. And also similar way on the equinox. If we have a vernal equinox in the northern hemisphere, we're gonna have a autumnal or fall equinox on the uh, southern hemisphere. All of this is reverse. Therefore, uh, this kind of between north and south hemisphere, we're gonna see it this condition. Any question about this? Okay, here the activity that we have on the length of the day that we have, how long is the day? For example, each city that you are living, you can check it based on the stellarium that we're gonna go and show the stellarium here. For example, if you wanna check the Chapel Hill on the summer solstice, if we're gonna check it, we're gonna identify the location. Then based on the what do you call it, the current location or the other area here, it's gonna gives us how we can provide here. For example, if we say search and identify the location and day and time, then we can go on the stellarium and we see it what month and day of the summer solstice is going to happen. Normally it is 6/12 or 6/22 or 6/19. Sometimes it changes. And we have to note that since the day and time window is also center of the stellarium main window, you may have to move it to side to see the sun. Therefore, sometimes it's very difficult to do that, but you have to make a notation on this note that is provided. And if the horizon is obscured by the tree or mountain, I think it's better to remove it those and see it very precisely how you can do it. And also, when you're zooming sun, you have to watch out on the main item that you have it. When you click any object here, like a sun, you see many different options here. It gives us different ideas about the coordinates and other thing, and we can look through it to see what's the what they call using 24 hours. We identify the nearest point, how much what to call it. We have the time and year that we are observing this situation in here. And please note that we don't need it to go much accurate here. Only we needed three significant digits. For example, 6.03 hours or 20.57 or 20.56, 20.6 or 13.5 is good enough for this purpose. Or you can put it more significant digit on this consideration. And then Stellarium also calculate the length of the day, but does it differently, resulting a longer value than you measure. This is the reason that, therefore, given this, you should ignore Stellarium daytime calculation. This is one of the important things you have to consider in here. And also, we have a sample calculation provided in here. For example, when you calculate here, you see example of the calculation. Convert decimal to the hours. If it is hours, it's 18 and minutes is 15. You have to consider hours plus minutes divided by 40, 60. 18 plus 15 over 60, it is 18.25. And that's for the percentage error you need to calculate. For example, you measure the value this month, but professionally, whatever measured is this much, and you put on this equation, and you get the absolute value positive and multiply by 100, we get around 1.5%. And this is a very simple calculation that converting the degrees and arc minutes to arc second and decimal degrees, and you can use it those as a kind of way to how to use it. And there is also guidelines provided here on the beginning how to you can do that. You can look through it as well on the beginning of the description in here.
So a quick clarification right there too for
Sure.
everybody. Just make sure like like a boss when he's going through this, 18 and 15 degrees isn't 18.15 because you have to convert that 15 minutes into what fraction of a degree is. That's why it's a 15 over 60. So it's an easy mistake to make to put down 18.15 when it's actually 18 point, all right, so 15 is a fourth of 60, so 18.25. That all makes sense?
Thank you. And on the next step that we are going here, and it shows the discuss significant source of the error. Again, similar way on the lab one that we identify what may cause the errors. We can identify what the cause of the error. And also here there is some keynote provided. The significant source of the error are typically difficulty identify sun center, given the sun glow and difficulty to identify the horizon and those kind of thing and mountains, for example, any place that you may have a surrounding area that is very difficult to identify the horizon as well, and those kind of sunset and sunrise also is not precisely given. I'm gonna show you an example in here that how it is defined on the constellation. Uh, if we're gonna do the how length of the day, how does the length of the day varies on the latitude and longitude? You can use the Google Map here. You can click here, Google Map, it comes, and you can consider any location that you have it to this activity. Therefore, if we go to the Google Map and check it, like the picture that you see it in here, if you are on the North Pole, it's gonna be in location. If you are on equator, you have here. There is many different circles parallel to the equator, latitude circles, and probably we're gonna have somewhere around Charlotte between 35 to in the northern, uh, for example, Canada and Toronto, probably 45. We're gonna be around this region. Therefore, uh, we can check it based on the Google how much um, Arctic circle gonna be, for example, here, middle of the northern hemisphere, like for example, Chapel Hill we are is about 35 degree or 45 is around Toronto or northern United States and the main state, and that's gonna show the near equator also. Equator is somewhere here. Therefore, we can identify 1, 2, and 3. 1 for the Arctic Circle, and middle is somewhere or either from North Carolina to the northern United States, and equator, number 3, and also midden of the southern hemisphere, some Tropic of the Capricorn, or again, Antarctic circle on the bottom is about minus 66.6. This one, we can check it. We use at different cities here. For example, here we're using Bisco Island, and we get the local time. And based on this information, we're adding the list, and we get the data from Stellarium. And then we provide the city, whatever we're providing, 1, 2, 3, 4, 5, the same way that we show in here. We choose a city here on this line, we want this line, and similar way, 1, 2, 3, 4, 5. And we get the data from Stellarium here, and we provide the longitude and either positive or negative on this table. And after that, we're gonna provide data from sunrise and sunset, and similar way length of the day that we calculate from the stellarium, the similar way. And therefore, based on that, after we finish, we can go to this website. And on this website, we're gonna provide a graphic tools that we have on this, we call it Astronomer. Astromancer. Astromancer is provided by Skynet and provide a kind of basic data, whatever we get it. For example, length of the day based on the latitude. And those, we're not going to go to this week, and we're going to go next week on this. But this is the last step of our lab here that we show how it's gonna work on our activity for the Earth. But if you have any question, let me know. But otherwise, on the next half of this session, probably either myself or John or both together, we're gonna go show how this gonna be do with similar cities on the Earth based on the experience with the Stellarium. Any question so far?
I have one question. It's not very much relevant to what we are saying here, but just a bit on the not philosophy, just the science of it. The tilt axis, the 23-degree angles. What is the range of this over the years? How do we know? I mean, it's not a constant angle. What changes this angle? What is causing variation in this angle in the long term?
Yes, yes, that's a good question. Thank you. Let me show it to you again. This one here.
It's
This
different.
yeah, this
And it's
angle.
yeah, go ahead.
Yeah, you see it. Okay, this angle is actually as is shown here, as you see it on any of the globe that you may have at your home or library or in a school. You see it. All of them is rotate like this. The reason is that this angle it is exists due to the what you call it, the when the solar system is created, this angle of the Earth is created this way compared to the surface of the rotation. If you see this plane of the rotation around the sun, we call it what we call it ecliptic. Remember last days we learned this is the ecliptic angle, and the angle of the what we call it the axis of the Earth is going to be 23 and a half, 23.4, something like that. And this angle is constant, but it's going to change in 26,000 years. Therefore, along our life, either 20 years or 10 years or 1 year of the, for example, if we're going to wait another year or so, not going to change. If we're going to wait another 100 or 200 years, not going to change. But this going to create a kind of, that is called it precision. Let me go to the, I think this NASA provide this very good on the good picture. Let me see if I found it.
Now, that's coming up real quick. One misconception a lot of people have, they think that our Earth wobbles around an axis and that gives us our seasons. But actually, it's just the opposite. As the boss is saying here, it is 26,000 years for this to precess once. So a lot of us know what a top is, and you've spun a top, and our Earth is like the most massive top you could ever imagine. It's so massive that it doesn't want to rotate its precession is so slow. It stays at basically the same angle. 26,000 years is a whole lot of time. So like our North Star, Polaris, has been that North Star for a long time. Now, a couple thousand years ago, it was another star. It's moved. Our North Pole has moved, but it takes thousands of years for a noticeable difference.
What causes this precession? Is it the sun causing it or some other stuff going
No,
on?
just the fact that something that spins.
Oh, angular momentum stuff.
It is. It's angular momentum.
Yeah. Okay.
It has a little bit when our thought is that the moon came from an object hitting the Earth, spinning us all up, and that spun out around the Earth. And in that time, we ended up with an angle. And we have so much mass that that angle didn't go to zero. It stayed there and has been rotating at that for a very, very long time. But we do have to have some precession. But again, it's a very, very long period for that precession. We're going to stay here for a long time. But
Yeah,
it is. We had an earthquake about, I don't know, a big earthquake down in South America, and it did actually change our axis enough that we gained like a second or two to the day, which doesn't seem like a lot, but it is, you know, I mean, over the year of a year, it changed it enough. So things do happen like volcanoes, earthquakes. The Earth is shifting and trying to get itself to zero, but it just has so much mass.
So there is history and like 26,000. Actually, we don't have any history. Like Australia used to be different. Summer and winter, Australia had some sort of snow going on, but we don't have that information, correct?
You're getting into geology now, you're getting into that. There's ways to kind of look back through the geological history and find how things have moved. And we can look at what we're doing now and kind of push it back and model it to what it has been. probably hasn't changed a whole lot since things have settled down. That angle has been that way probably for a long time, what it sounds like.
Thanks.
Good question.
And thank you. This one is to illustrate how it happened. It is kind of probably you may have a gyroscope in the childhood. You just spin it and rotate it. It's gonna rotate as kind of moving around like this. But as based on the what to call it, the different way of the mechanics of the solar system, this rotation and the distribution of the mass and the other things that is gradually gonna move. And not only that, normally we learn that the Earth movement is just have two movement. Is one uh, around his axis. This is his axis here, and one around the sun. This is the second axis. But actually, the Earth movement, we have almost identified 7 or 8 or more different movement that they have. It doesn't mean that this gonna be exactly like a circle here. It's gonna be some variation here. It's not gonna be very perfect. And also same way around the sun. Although on the simplification on the schools, we just showing as a circle, but actually it's not perfectly circle. But the thing is that here, right now, as you see it on this picture, right now, if you extend this one, it shows very close to the Polaris or North Star. And when you identify the North Star, you can identify the close location that is Earth axis gonna be located. But about 14,000 years later, it's gonna be close to the another star, Vega. And before that, in the time of the ancient Egypt, there was some studies on archaeological investigation is happened that they call it that is closer to another star. They call it Thoban. Therefore, that Thoban was at that time actually the Earth axis very close to that star on the northern hemisphere. Therefore, that's the reason that we call it. And on the South Pole, we don't have any specific star alongside. If we go to the southern hemisphere, there is one of the difficulties to find out and orient your telescope is that you don't have very specific star like a Polaris you can orient your telescope and take a picture. And that's one of the key things that you may observe. But this is kind of very close to 23.5 degree, and it is gonna happen every about 26,000 years. And those, if you have a time, I'm gonna provide some brief history of this based on my investigation, and also some actual consequences that we never noticed that this made 26,000 may cause. Okay, and go back to our work. Any questions so far?
Thanks.
Okay, let me go to the Ethereum app that I mentioned. And the first thing we close this, become like a night, and then we go, as I mentioned, first thing we should do the location. For example, we just tell me, you just give me some city name you wish to do. For example,
Chicago.
Chicago. Okay. Chicago, Central United States. Okay.
Mhm.
And when you click on that, that's gonna identify. And what's the latitude is? It is no, that's not correct. Shouldn't be that one. Uh, uh, Here is better. You have to watch out that sometime when you click it, you identify your previous location. It's gonna be good. Again, it disappeared. Yeah, here is. Uh, Here you have to click auto select the landscape that you have it here, and then okay.
I think we're not seeing your image. We're just seeing the lesson.
Oh, let me share it again. Yeah.
You change your screen. And also my Stellarium, I'll try to get it up too, boss, but I'm having a little bit of challenge with my dual screens. It's doing weird things to Stellarium for me.
Yeah,
Just
it is difficult. Hopefully you see it right now. Do you see it? Okay, here you specify the Chicago here. You have to watch out here when you can identify here Chicago and then find it, or you just scroll down the arrow here, you find it, and then it gives you the coordinate. Latitude is 40.11 minute. Therefore, to convert it to hours, what you're gonna do, 40 plus 11 divided by 60, and that's gonna transfer it to the hours unit. And also here, longitude is 76 18 minutes, degree 18 minutes. Therefore, it is western. Because it's western, it's going to be minus. It's going to be minus 76 plus, minus 18 divided by 16. And whatever number you get it, that's the kind of coordinate you're going to have.
Mhm.
And then you're going to look through the, what to call it here. When you see it, there is some information provided for Chicago here. And that's kind of various item that you have on this object, dependent on the object that you're choosing on the sky. For example, assume I choose the sun. Okay, I close this one. This is the location of the sun and gives you different values in here. And it gives daytime. As I mentioned, daytime is not very accurate here. You have to watch out on that consideration. And also, it shows the 10-hour, 57-minute daytime. And also, the other information given, for example, sunset and sunrise, and morning twilight, and evening twilight. And normally, you have to watch out on here and also give some apparent diameter. Is you see at 32 arc minutes, almost the same size of the Earth moon. It is both of them is around 30 minutes, and when they are very close to each other, sometimes it goes 32 and 31 on also moon because of the geometry of the orientation and the orbit, and sometimes it goes very close to each other. When they are the sizes, apparent sizes of the moon and the sun is the same, or that condition happen, then lunar and solar eclipse are gonna be what to call it, complete.
Perfect. Yeah.
Yeah, and but when it is not the same, smaller, that's gonna be partial solar or lunar eclipse. Therefore, that's the reason that based on the geometry of the Earth and Sun and the sky, as you see it, I have to bring it this one in the center because it always moves it around. Another thing that you have to watch out in here, the consideration, two things. When we call it sunlight and sunrise and sunset, we're just thinking one single time or single specific time. But actually, twilight is defined in astronomy. They have three different definition because of the different reason. Normally, when assume this is a horizon and sun, it comes on this location. When center of the sun on the imaginary line of the horizon exists, we call it sunset. But actually, sun is not a point; it's a circle. About how much degree is about 30 degree, half a degree or 30 minutes. Therefore, a part of the sun gonna enlight the sun. As you see it, the very beautiful sunset or sunrise because of that partial light that is reflected on the atmosphere. We see it reddish color. But when the center of the sun goes around 6 degrees below the surface, again, we're gonna see some reflection of the sun, and the sky is not dark anymore, but gradually goes darkness. But when it is about 6 degrees under the surface, we call it uh, uh, civil twilight. It means that from civil tradition and the contract that we decided when define it, we call it civil twilight. And when it goes around 12 degree below the center of the sun, 12 degree below the horizon, we call it nautical twilight. That is mostly used by the shipping and the kind of explorer in the about 1,000 years before they invented that twilight for their own purpose. But the astronomical twilight is the one that the sun center goes around 18 degrees below the horizon. And therefore, that question comes, what the sunset and sunrise we're going to define. That's going to be kind of tradition. We have to decide what actual daytime is, what actual, what to call it, uh, nighttime is. Normally, we use it about this 6 degrees. As you see it here, morning twilight and evening twilight that is identified here. It is a kind of H minus 6, H minus 6. This H minus 6 degree is defining the civil twilight when center of the sign goes 6 degrees below the horizon or reach to the 6 degree before the horizon on the morning side. That's kind of very brief description of the what the twilight, why we're using 6 degree here to identify the amount of the day and nighttime. Any question on here?
Mhm.
Couple quick comments real quick to do this. Good job going through all this. As always, can keep straight civil and nautical, because if you're on the ocean, there are no trees, there's no mountains. You have the lowest horizon you can have. And that's why that'd be the later one of the two. Also, same thing about is refraction, which is happening on the atmosphere. And I be careful I don't go too far on this. But like if I have my glass right here, it looks like it has no edge to it, no thickness to the glass. That's because the liquid inside is being refracted around. That when we see the sun set, if you've ever been on the, like in the Gulf or somewhere in the ocean, you see the sun setting into it, and you see that ball, that half-degree ball dropping to the horizon, just realize because of refraction, it's probably past the horizon already. We're seeing light that's been refracted over. And that also gives us colors, the fact that it looks so red. And, people always, what's the color of the sun? It's easy. Oh, it's red. No, well, that's the refracted light we're seeing is the red light. The blue light is traveling straight through. We've seen that scattering in the sky during the day. And the colors of the sun will change. They say if you go on a mountain high enough, if you watch the sun going down, you actually see what's called a green flash. That'll be the colors come back around and you actually see one more color as it goes. So it is kind of nebulous on where this time is. It's going to fluctuate where you're at, and it depends on our latitude and longitude, but as much as about refraction is a big part of this as we do it. And honestly, the sun to us looks white. It looks very white. It has a red, green, blue distribution. And if it's strong in any color, it's actually strongest in the green. But nobody'd ever say the sun is green unless you knew that's what it resembles as a black body. So my 2 cents worth. Doing great, boss. Any other questions?
It was good.
I hope this activity that we're gonna have on the what to call it. Let me share it again. The place that we had.
As you're pulling that up, one more thing I'll throw out real quick. I'm good
Go
at
ahead.
useless data here, trivia. But the geographic, and we look at the poles, the North Pole, we're using the geographic poles. The magnetic poles are close, but they're not exactly in the same place as geographic. I think it's over 1,000 miles apart between the two. And actually, the magnetic poles are opposite the geographic poles. So the North geographic pole is closest to the south magnetic poles. And we can think about this when you look at a compass, the compass has a north magnet and has a south magnet on it. The north magnet will point towards not the north, it'll point towards the south. That's how it's designed. So if we define a compass as having a north and south, then we also define the magnetic poles of the Earth with the south on the top and the north on the bottom. But what we're doing is mainly using the geographic, so people usually don't get too far in the weeds with that one. It's kind of neat to know.
Why? I mean, how do we do? I mean, how do you define the magnetic south and north? I mean, why they have to put south in the north geographic ones?
Yeah, well, actually, a lot of maps will label the south magnetic pole as the north magnetic pole. People just don't know. And it's convenient. It just gets confusing anyways. But when we defined what a compass was, we defined the poles the other way around. Really, a compass should have a south on the top and a north on the bottom. But who'd understand that the south points to the North Pole and the north points to the South Pole. And if you do any orienteering where you're walking around compasses, you'll notice that it doesn't always point where you think north is because of ores in mountains and ground and like that can affect this. I think it's part of that thing too. The internal part of the earth is still churning and coming to equilibrium is why those two aren't quite lined up.
I see.
Thank you, John. Thank you for questions, Mike. The other thing, the main thing that remember on this lab that we're gonna do, I'm just reviewing the kind of objective that we have. We're gonna determine the length of the day changes on latitude and season. That's the one that I showed one example for the Chicago, and then you can do it for various locations here, like I mentioned 5 points, 5 city you decided on the various place on the earth. And a similar way, you can change the date and time. For example, on the different seasons, on the summer, winter, and the season, you check it. And then you determine height of the sun on the sky on the midday, changes based on the latitude and the longitude. That's the same thing that happening on here. For example, and the last one that we're gonna go next week is about measuring the Earth diameter, and we're gonna have some short view of the measure of the Earth that is done from Eratosthenes and about 20 more than 20,000 years ago until now, that they see how they intuitively they measure the Earth diameter by the ancient scientists on this time. Therefore, this is kind of this week is mostly we focus on to get the latitude and longitude and also the height of the sun and information about the length of the day, that you can do it accordingly on the description of the web assigned here. And any question you may have, you just either send it by group contact by John or myself, or by email. Just feel free if you had a question or trouble, let me know. And also I mentioned I'm gonna send that email again reminding if any of you doesn't have access to the web assign, just please send me the PayPal or a Cash App or Venmo, and I can send you the money as needed for the registration for the web assign as well. Any question?
Yeah, thanks.
Okay, we are almost 7 minutes left from our session. I believe this week and next week gonna be very short because we don't have much complexity and very simple on the Earth and the season. And it is gonna be our initiation point for the next week's lab 3. We're gonna have more go to the dynamics of the solar system to calculate the orbits and also moons of the planet. That I hope it's gonna be very exciting moment on the lab 3 as well. But it's actually on the Earth, I feel it. We can connect it very easily with the Earth with a simple way. For example, in the old days, probably you heard on the history that they just attach one stick on the ground, or we can do it right now and see it, how the shadow of that stick gonna change during the day from the sunrise to the sunset. And that's going to be very plenty and good to exercise and do activity. Okay.
Just in the
If you
interest,
go
I know
ahead.
we have a couple of more minutes. Like, just I have a question. I was reading something about like two different masses when one of them rotates, the other one also rotates too. It's something defined Barry center. The masses, if they're in the same order of magnitude, that Barry center causes strange things. Like when we are just rotating around, just if we take a large mass and then we rotate around us, the mass takes us in phase and out of phase with its rotation. So that has some effect on sun with respect to Earth as well, correct? Like when we are moving, so the motion of the circular motion, there's also motion in the normal to the circle as well. And there's some sinusoidal motion. I don't know, just is that,
Yeah,
have you,
it is very complex. As you mentioned, we assume all these celestial bodies are on the as a kind of acting as a point, but they are not point, as a solid,
correct,
a very big solid. For example, in the sun gonna be a million times greater than Earth or so, and therefore it is not comparable. And also all of them, we call it that is kind of very go on the detail on the two body or three body or multiple body celestial mechanics. That is not a subject of our study in
correct,
this
yeah,
course.
yeah, yeah.
But the thing is that any of them it's gonna be impact each other. And also one of the a quick example that is right now the NASA and the ESA and CISA, Canadian and the European and American agencies, they are working about the impact of the asteroid on the Earth. For example, the reason is that they just send some spacecraft to the asteroids in the last few years, and next year another one ESA gonna check it. They just at impacting one a small object like a spacecraft to the one of the asteroid to see how the orientation or movement or rotations or other parameters going to change. Those is gonna is active way, but normally you're right. If you have several objects nearby, that gonna impact. For example, tide that you see it on the oceans caused mainly by the effect of the moon
Mhm.
rotation, because the moon is
Closer, yeah,
small, well,
yeah,
very close to us. Therefore, it doesn't impact the solid body of the land, but impact the liquid because that is stretches back
yeah,
toward itself, and that create a kind of tidal in the open seas and the oceans. That's normally is very complex, but we are assuming on the simplicity, all of them is a point, but they are not point. Neither sun a point, neither earth, neither of the object on the world
correct.
is a point. But that is kind of simplification to understand. And if somebody interested to go in more detail, it can find out how those uh, simplification may change when we actually check the entire body of the object on the concentration.
Correct. Yeah, I mean, for search for the title stuff, yeah, it's very complex. I mean, the whole water goes up, back and forth. Yeah.
Yeah.
There's
Okay.
something to
Thank
think
you.
too, that most of the well, a good percentage of the stars you see at night are actually binaries. And you think about how lucky we are not to be in a binary system. That the Jupiter is the closest mass body to the sun, and it's still 1,000 times smaller than the sun. But it is right that the sun is being affected by Jupiter, and Jupiter affects the sun. It's both ways. The kind of the cool thing in like just a simple two-body problem is if you treat the one object as the center, you work out all the physics, it works out very nice. And then you can work the other one as just a two body, as it being the center, it works out very nice. When we get into multiple bodies, that's where it does get a little trickier. And the modeling over long periods of time is what we look out for. So like this asteroid that's supposed to come close to the Earth, that can in the near future they found, the concern would not be so much even an impact, but just coming close. We don't want it to disrupt anything that's going on. That'd be a concern. But thankfully, the asteroid is very, very, very small. That an impact would be our biggest concern, you'd think. But it's like everything's connected. Thankfully, things going slow, and there's a lot of empty space out there.
Correct. I read one thing you just mentioned, John. So most of the stuff, the stars we see, they're binaries. Like there's only two bodies going around each other. Is that what it is?
Well, there'll be a couple types of binaries. Some are visual binaries, but it looks like they're next to each other, but one's way far away, got that parallax thing going on. But there are some that are gravitationally bound to each other. Yeah, there's binary systems like that, or one star eating another star and things going around. That is very common. It could happen. And even there's theory on our planets that Uranus, Neptune, and Jupiter did a dance, that the asteroid, where the asteroid belt is, it makes sense. I saw it was a talk at the AAS one year about it makes sense that Uranus was inside Jupiter's orbit at one time and Jupiter spat it out basically, and we still kept it. So that's the stuff that astrophysicists try to do, is the long-term modeling. And it's tough, to figure it all out.
Nice.
And also another example is the Pluto Charon. Pluto Charon is a dwarf planet, but they are almost the same size, close to each other. And also, New Horizon discovered about 7 or 8 years ago or 10 years ago. But in addition of that, right now we know that this is not binary only. We have 5 or 6 smaller objects around them. It is not like one single object. And that's amazing that always we learn more, and we know that all the data improve on the science more
Yep.
often.
True.
Yeah. But if you want to know more about our sun, our star, I'm going to put this in the chat, but you Google Soho and the sun, there's a lot of activity going on right now. If you just want to check it out sometime, there are explosions off the surface. And this is you'll get into Soho through NASA, and it shows the sun in different colors and the explosions and all the things that it's doing right now, because we're at maximum. It's a really fun time to look at it.
So what is Soho? I don't know what is that.
SOHO and sun.
Okay.
Just Google those two, it'll come up.
Okay.
And it's got all types of videos, the recordings they've made in the last few days, images, what it looks like today, sunspots and flares. A lot of really interesting stuff about our star, because we're churning on it too, and it's trying to churn itself. So a lot of activity going on.
It's actually a picture of the sun alive, whatever you see it at the moment. That's the kind of opportunity the NASA provided by Soho alive. Everybody can look to it.
Thanks.
Okay.
Any other questions? Okay.
Yeah, we are on top of our, and glad everybody joined the meeting, and hope you have a wonderful rest of the day, and see you next time.
Thanks.
Thank you.
Okay, thank you.
Bye. Bye.
Bye.
Thank you.